Today we're talking about fixed parameter tractability, which is a paradigm in algorithms. There are many natural problems for which we currently don't know of any polynomial time solutions. These are problems which we need solutions for because they arise in very natural situations, such as bioinformatics, vehicle routing, and scheduling. But we don't know how to solve them efficiently currently. So what are some ways of dealing with this? We can try a few different approaches. One is a heuristic approach, which is commonly taken in the field of artificial intelligence. Another is approximation algorithms. Approximation algorithms give polynomial time solutions at the cost of the optimality of their solution. However, this is a very mature field, so it's difficult to make progress on research questions in this field. One thing we can do if we still want exact solutions is we can relax our notion of tractability. Traditionally, problems for which we have polynomial time algorithms are considered tractable, and all others are considered intractable. But this need not be the case. So this relaxation leads to the notion of fine-grained complexity. So there are a few different ways in which this can arise. If the runtime of an algorithm is order c to the n for some constant c, we can try to improve on c. If we get c from, say, 2 to 1.1, then this can yield significant performance improvements in practical applications. Another thing we can try to do is we can try to find sub-exponential algorithms for our problems. These are algorithms which run in super polynomial time, but are significantly faster than exponential algorithms. So an algorithm running in time order 2 to the square root n would be an example of a sub-exponential algorithm. Another thing we can do is instead of having the complexity of an algorithm be a function of the size of the entire input, we can have it be a function of multiple parameters of the input. So indeed, parameterized complexity is a measure of complexity of problems with multiple input parameters. So this arises very naturally for many problems. For example, for vertex cover and clique, the input is not only a graph, but also a parameter k. So it'd be natural to consider this parameter separately in our analysis of the complexity of the problem. So in this case, we change our definition of a language from a subset of sigma star to a subset of sigma star with a Cartesian product of the natural numbers. And we say that a language L, with this above definition, is fixed parameter tractable if we can decide whether instances are in L in time f of k times a polynomial in the size of the rest of the input. Here f of k can be any computable function whatsoever. In general, for algorithms for which we don't have polynomial time solutions normally, f will have to be super polynomial. One important thing to note is that f can only be a function of k and cannot be a function of the size of the rest of the input. So here a function of the form k to the k times n cubed would be a valid function, and we would call it fixed parameter tractable. But a function of the form n to the k would not be. And the corresponding complexity class that follows from this is called FPT. So an example of a problem that is fixed parameter tractable is 3-sat when parameterized by the number of variables. So here the input to our algorithm is a 3-sat instance and k, the number of variables. And our algorithm tries all 2 to the k possible assignments to the variables. If any assignment is satisfying, we accept. Otherwise, we reject. And this algorithm runs in time 2 to the k times n, since there are 2 to the k possible assignments, and for each assignment, we do O of n work to verify whether it is a satisfying assignment or not. And so indeed, 3-sat is fixed parameter tractable.
So now it's important to also discuss problems that are likely not in FPT, that we can't fix a parameter on. So one example is k colorability. In this instance, you're given some set of k colors and a graph. And essentially, you want to color every vertex with one of these k colors, such that no 2 vertices that are the endpoints of an edge share the same color. Now, it's a well-known fact that for the fixed parameter k equals 3, this problem of 3 colorability is NP complete. But if we thought that k colorability was an FPT, then this would mean that 3 colorability could also be solved in polynomial time. Now, this would imply that p equals NP, and with the current state, we don't believe that this is the case. So K colorability is likely not in FPT. So now that we have some foundations of what FPT is and what it looks like, it's also useful to discuss the generic methods of research in the field. So in dealing with FPT, there are some established techniques for how we approach particular problems. Some of these techniques are called bounded search tree and kernelization. And essentially some of the goals of these techniques are to shrink our solution space in an efficient manner so that we can get an exact solution. Now, with research currently, you're very unlikely to be able to create a new technique that applies generally to various problems. Instead, a lot of the research right now focuses on combining results from relevant papers to a particular domain and adding in an additional trick to these results in order to get some algorithmic improvement. Now, it's also interesting to note that in the field, the newer problems are easier to work on as compared to older problems. Now, this is because with older problems, a lot of people have tried and failed on improvements to these older problems, so someone else is also very unlikely to make huge improvements. So newer problems that are constantly being updated and have some algorithmic improvements are a little bit easier to work on. Now, like other theory research and other research in general, FPT does face its own challenges. The biggest challenge with FPT is that finding new algorithms is difficult, and it may never work. If you think back to Professor O'Donnell's presentation, he discussed that you might sit down for a month or several months on a particular problem, and you might not make that much progress. So in a sense, FPT is a very high risk, high reward area of research in that you might spend some time on a problem where maybe no gains can be made, and essentially some of that time is wasted, or you might have a groundbreaking result in some interesting problem, which then can be used in a practical setting. However, another issue with FPT, or another challenge that people face, is that sometimes you might have some algorithmic improvement, but the solution might be still impractical in some settings. So now in talking about FPT, I'd like to talk about some recent advances in the field, particularly at CMU. Here I've noted two papers by researchers here at CMU that have done research in FPT and also approximation algorithms. So in these two papers, what we see is FPT algorithms in combination with approximation algorithms to achieve better results than just approximation algorithms alone. And as we'll see in the next slide, this is sort of where the future of FPT is going, and it's some of the most common research nowadays. Now also in non-CMU research and just in general, there are also a lot of advances in small algorithmic improvements in FPT. So that might be achieving some better runtime in some problem, building off some previous paper. And some of the most important advances, however, recently have been in showing tight lower bounds for particular problems, which essentially tells researchers you're not going to do better than this particular result, and it may encourage research into new areas and areas where we can make more algorithmic improvements. So then finally, talking about the future of FPT and what that looks like is that there are currently a lot of open problems in FPT, as it is a relatively recent field compared to approximation algorithms. And as a result, a lot of the open problems are talking about, can we make difficult problems runtimes a little bit faster? So is there a faster 3-sat? Can we improve on the exponential running time of 3 coloring? And as I talked about before, one of the biggest areas of research is in the combination of FPT and approximation, as these fields separately are starting to get a little bit saturated in terms of the research that's been done in the past, but there's still a lot of open research in the combinations of these two. So that concludes our presentation of FPT, and thank you guys.